It is great to see you all here. And we're going to welcome Yuka Fujii today, who joins us to continue our Rocky Worlds discussion series. And a reminder of etiquette, please use your full name and keep muted throughout the talk, and turn on your video if possible, asking questions at the end. So I will now hand it over to Yuka, who will talk to us about multi-facet characterization of potentially habitable worlds with future telescopes. Take it away, Yuka.
Okay. Hello, can you hear me? Okay.
Yes.
Okay. So, hello, I'm Yuka Fujii from NAOJ, and thank you very much for having me today. My main research interest is exoplanet characterization, and I'm particularly interested in how to constrain the planetary surface environment of potentially habitable planets and also other rocky planets from observables. Today, I'd like to introduce some studies on and exploration on the observable features of rocky planets. As you probably all know, around 20 potentially habitable planets have been discovered so far. And each time it's discovered, various illustration can be drawn. But of course, they're all artist impressions and the reality could be very different. And for most stars, the only information we currently have is orbital distance and radius and or minimum mass. The ultimate goal in the coming decades is to understand what these planets really look like. Some of them could be Earth-like watery worlds, maybe Mars-like worlds, and maybe icy worlds. Unlike planets within our solar system, the information we can obtain about exoplanet is very limited. Let me briefly introduce several techniques to prove to understand and characterize planetary surface environment. First, transmission spectroscopy is a technique to probe the wavelength dependence of the apparent size of the planet, while the planet is just in front of the star. This can tell us the wavelength-dependent extinction properties of the atmospheres, which are the clues to the atmospheric compositions. Another useful technique is to detect planetary light using eclipse. And the flux difference between during the eclipse and out of eclipse can be attributed to the planetary emission. And these two techniques try to identify the planetary signal in the combined star and planet spectrum, and will be the main approach in the era of JWST, and also ALT will try to do this. On the other hand, direct imaging can in principle characterizes planets in a wider parameter space. While direct imaging has been successful for larger, very luminous gaseous planets, direct imaging of rocky planets will be the main scope of future telescopes, including ELTs and also space-based a proposed mission, Habitable World Observatory, or LIFE mission. And so having these capabilities in mind, the first thing we probably think of is taking the spectra of exoplanets. And here, the upper panel shows the model transmission spectra of Earth, where local peaks corresponds to the absorption band of the atmosphere. And the lower panel shows the spectra emitted by Earth, taken from Robinson et al. 2011, where the shorter wavelengths, the bump here corresponds to reflected light components. And in the mid-infrared, you will see thermal emission from the planet. And in these spectra, we can see fingerprints of several atmospheric molecules. And the one of the strongest features come from CO2 in the case of Earth's atmosphere. And here you can see both in transmission and in this emissions spectra. Also, H2O features can be best proved in the scattered reflected light components. Also, the presence of oxidizing species like ozone or oxygen and reducing species like methane have been recognized as biosignatures. Atmospheric composition as proved through spectroscopy is certainly one of the key and necessary observable signatures of rocky planets, and they provide piece of evidence on the surface environment as well as their formation and evolutionary pathways. On the other hand, there are also other pieces of information which is also available. And this includes the wavelength dependence of the continuum, or in other words, the spectral features broader than those of atmospheric molecular features. And we could also use the time variability. And today, I decided to put more emphasis on exploring the latter, these cases, as they are relatively infrequently discussed, I think. And while they may or may not be harder to detect, they have a potential to provide information of the planetary surface environment complementary to the atmospheric composition. And also, as we will see later, these features cannot always be sufficiently modeled using a simple 1D model and requires the understanding of the planet as a system. And so there will be some rooms for further discussion between exoplanetary science and the solar system scientists. And so this will be relevant to this discussion, I thought. And I'm also going to minimize the discussion on the detectability. I'm not going into the issues related to, for example, the instrumental systematics and the stellar activity. Okay. Having said so, let's base our discussion on the actual data from recent data from JWST. Among temperate or warm, relatively cool rocky exoplanets, the main targets in the area of JWST will be those around nearest Loma stars, like the TRAPPIST-1, the famous TRAPPIST-1 system. This is a very compact system around very faint stars, very low mass stars. Oh, sorry. And there's 7 rocky planets in the TRAPPIST-1 system. And recently, JWST observations of broadband thermal emission from the 2 innermost planets, TRAPPIST-1b and 1c, have been reported. These 2 planets are likely too warm to be habitable, but still much cooler than the typical targets and showing the power of JWST. In these 2 figures, the observed data are highlighted in red, the point with error bars. And they are overplotted with theoretical models. They found that, in particular for TRAPPIST-1b, are not likely to contain thick atmosphere. And this conclusion comes from the fact that this observed thermal emission is much higher than the theoretical line expected for full heat redistribution. As shown, what I mean by that is that, as shown in this figure in the upper right, the date side of atmosphere-less planets like Moon tend to be hotter and brighter in thermal emission than Earth-like planets, which can redistribute the instant energy efficiently. And so this very bright day side suggests that the atmosphere is likely to be thin. And according to the previous models, the it's likely to be thinner than, for example, 0.1 bar. And because this overlaps with CO2 absorption features, and this also indicates the absence of CO2. And so this does not have a very thick atmosphere. Oh, sorry. And perhaps the planet never had accreted volatile species, which is also likely because the orbit is very close to the star. Or they may have once accreted some volatiles, but have lost under substantial, because the M-type star would have been subject to intense XUV, especially early on, and prone to substantial atmospheric loss. And so the planet's after atmospheric mass loss remind us of some solar system rocky planets like Venus or Mars, which are also considered to undergo atmospheric loss. In particular, Mars has tenuous atmosphere, which is consistent in a sense with the infrared thermal emission observations. And so this motivated us to think about a very different, the observable features of the planets very different from the Earth. And Mars could be one such benchmark cases. And motivated by this fact, we recently analyzed the Martian data to reconstruct the near-infrared empirical transmission spectra of Mars. And as an example of the planet having a very thin atmosphere, and also as an example of dusty wars. And this work was led by Aoki-san from University of Tokyo. We used the occultation data of Martian atmosphere obtained with ExoMars trace gas orbiters NOMAD detector. We combine the solar occultation data at different locations to obtain the average transmittance as a function of altitude and wavelengths, and translated it to the transit depth. And so y-axis here is the effective height, which is the apparent thickness of the atmosphere when observed in the stunt path, and also is proportional to the transit depth. Because Martian atmosphere is mainly composed of CO2, we clearly see its features around here, around 2.7 micron. And this itself is relatively strong features because it becomes optically thick around 40 kilometer, which corresponds to 10 to minus 4 bar. And however, even though the atmosphere is thin, the Martian atmosphere is thin, it's optically thick near the surface because of the dust, and therefore the signal is much suppressed, as shown by this offset. So interestingly, we also see the broad signature here around 3 micron, which is attributed to H2O ice. And therefore, although we do not usually see Mars as a water planet, the signature do look like a planet having H2O. H2O ice feature itself is not directly relevant to TROPICS-1b or 1c because of the high effective temperature, but could be relevant to cooler planets. And so in fact, this empirical transmission spectra is based on the data in the quiet phase. The transmission spectra based on the data set during the dust storm is shown by this red line. And you can see the overall larger apparent size or the larger effective height of the atmosphere. And correspondingly, a CO2 feature becomes weaker. On the other hand, H2O ice feature actually becomes larger. And this is related to the vertical transport of H2O that becomes more efficient during the dust storm, as pointed out by Aoki et al. 2019. And this shows the evolution of water vapor mix, the vertical profile water vapor mixing ratio that corresponds to the storms. Although the variation itself is could be challenging to detect, such dynamic nature of transmission spectra is probably worth attention. Okay. So while JWST is advancing the characterization of relatively small planets by the identification of planetary signal in the combined star and planet spectra, the more comprehensive survey will be conducted with direct imaging. And so let's move on to the direct imaging, firstly focusing on scattered light. So here I am again showing the Earth's reflectance spectra from Robinson et al. 2011. So aside from these molecular features, we can recognize a radial scattering slope at shorter wavelengths. At longer wavelengths, we can see some gentle slope toward the that becomes higher, higher reflectivity at longer wavelengths. And this is related to surface features. This can be compared with the reflectance spectra of representative surface types of the Earth. And you can see, as shown here, as you can see, some soils and also vegetation have a very high reflectance at longer wavelengths. In other words, ocean planets may not produce this kind of slope, this overall patterns with this slope. This figure probably shows it more clearly. The bottom panel compares the top of atmosphere reflectance spectra with varying assumption on the surface reflectance spectra, as shown in the top upper panel. The difference in the surface reflectance spectra appears around this region because this region, anyway, yes, region. Fei Wang, who is now at the University of Hertfordshire, and we examine whether such wavelength dependence of surface color could be constrained in the retrieval framework from the disk integrated spectra. And so we made mock spectra of an Earth-like planet. A typical retrieval analysis focuses on estimating atmospheric composition, assuming gray surface albedo. But in this work, we parameterize the wavelength-dependent surface reflectance by interpreting the albedo at 3 bands: blue, green, and red. The lower panel shows some of the results. The black line here and here corresponds to the input reflectance spectra. The shaded region are the estimated reflectance spectra. So under realistic assumptions of cloud optical parameters, the trend of the surface reflectance spectra can be retrieved together with some parameters of atmospheres. So this is about the disintegrated spectra. But in fact, the surface of the Earth is very heterogeneous. And the reflectance spectra, the disintegrated reflectance spectra changes in time according to the spin rotation due to the change in the illuminated and visible region. And so here is the multi-band diurnal light curves of the Earth at various wavelengths observed from space by the epoxy project. So different colors corresponds to different wavelengths. Such patterns, according to rotation, could allow us to recover the rough longitudinal map of Earth's surface compositions. And that was demonstrated by these papers. And this comparing to the actual surface of the Earth, the red color, the map of the red color, or this color, can represent the original ground truth of the Earth's surface. And this kind of analysis also tells us some detailed features of the planetary surface. The possible challenge is the signal-to-noise ratio, as it requires high time resolution, and we will have to bin the spectral elements and consider the broadband variability. But we also want to note that the presence of lead color and dark color do not necessarily corresponds to the continents and ocean. Oh, sorry. For instance, Mars are also red, and it has a large scale patterns of red region and also dark region shown here. And so if it had an atmosphere as dense as Earth and that as the blue color, it might end up with some colors somewhat similar to those of ocean and continents if limited data are available. And as it rotates, it also shows some color variations, especially toward the longer wavelengths. As well known, but in fact, the colors of the Mars itself is also very interesting. As well known, the red color of the Mars is attributed to iron oxides or rust, and the bright region are largely attributed to the fine-grained materials, typically smaller than 10 micron, which are mostly created by wind through the mechanical weathering. And the upper light figure showed that the smaller particle size result in higher albedo due to efficient scattering. And so current understanding suggests that the Martian dust probably formed in the presence of liquid water and weathering, so it's kind of related to the past presence of water. So such information is also very important to interpret to decode what the surface environment is used to be. So coming back to the Earth, what are the other observable characteristics? The presence of ocean is, of course, of a particular important. So aside from the color of planets, another possibility that has been proposed is the specular reflection of water. The liquid water or liquid surface in general has a mirror-like reflection properties, like illustrated here. The reflectivity is highest when the incident angle is low. And so in other words, it's brightest when it's shown in the grazing angle, when it's illuminated in the grazing angle. And such geometry corresponds to the situation where the planet is observed at the crescent phase like this. And at crescent phase, apparent albedo increases. And also the overall spectral shape also changes, as shown in this figure taken from Vincent et al. 2018, because the increased, so the black line shows the crescent the reflectance spectra at the crescent phase with ocean glint. Because this overall change, the gray spectra corresponds to the crescent phase, the spectra at crescent phase without glint. The change in this overall reflectance spectra is because of the very efficient scattering by ocean, which is prominent at longer wavelengths, because at shorter wavelengths, the atmospheric scattering is more dominant. While observing planet at the crescent phase itself is probably challenging, this is also an important clue to the presence of liquid water. Another potentially interesting characteristics of ocean-covered world is their active hydrological cycle. So look at this figure, and this shows the the atmospheric water vapor on Earth. It's clearly seen that the water vapor is most abundant near the equator, or near the tropical convergence zone. H2O, a water vapor, is also vertically heterogeneous as well due to the cloud formation. And such characteristic heterogeneity is very different from other well-mixed gases like oxygen and CO2, and could in principle be probed by variation of the spectral shape as at the change due to the change in illuminated and visible area. So in reality, habitable planets usually have water clouds, and so the identification of such signatures are challenged. However, our analysis on the disk-integrated near-infrared spectra of the Earth, again obtained by Box mission, identified the difference in the time variation between water vapor absorption bands and other well-mixed gas species, mixed species like CO2, which can only be explained by the heterogeneous distribution of water vapor, which is the red line shown here, as compared to the dotted observed data. And the precision necessary to observe such feature is higher than the detection itself, but this could also provide complementary information to the planetary surface. So while we have considered liquid water, the other possible state of water wall is the snowball state. If the greenhouse gas in the atmosphere is not sufficient, habitable zone planets could be found in such state. And Earth itself is also thought to have gone through snowball state in the past. In this case, an interesting case could be made by icy Galilean moons. Their surfaces are mainly composed of ice, and their near-infrared reflectance spectra shows prominent features of water ice, and therefore could be relatively easily identified. Looking into the shorter wavelengths, however, the surface of these moons appeared relatively red, although the fresh snow is usually very white, as you know from this picture of the South Pole on the Earth. And this coloration, this color is it's due to space weathering, and the icy surface becomes darker through annealing and contamination by meteoric materials. And so permanently icy planets may not be as white as we might naively imagine from the picture of the South. And also, but among them, Europa is notably bright, especially in the leading hemisphere. And the leading hemisphere is known to be, the surface age of this bright region is relatively young, and so suggesting recent tectonic activities. And so the bright surface is one of the indicators of young tectonic age or active hydrological cycle. Another notable feature of Galilean moons is albedo dichotomy between the leading and trailing hemispheres. And this phenomenon is likely related to the fact that these moons are tidally locked to Jupiter, and Io has volcanic activity, and the Io-derived sulfur-containing plasma trapped in Jupiter's magnetosphere preferentially hit the trailing hemisphere because the angular velocity of the Jupiter's magnetosphere is larger than the orbital angular velocity of the moons. And so this kind of process, so this figure shows such configuration. And this observation suggests that the volcanic active body in a complex system may affect the surface materials or the colors of the other planet within the same system. And probably the most prominent example is Iapetus, which has very bright surface and also very dark surface, which is also related to the volcanic activities of the other moons in the same system. So considering these processes provides some non-atypical processes that alters or that can be proved from the surface albedo information. Okay. Finally, I'd like to touch on thermal emission briefly. Here, I'm showing the thermal emission spectra of the Earth, Venus, and Mars taken from these Countnecker 2017. And all these spectra show prominent absorption features of CO2, as mentioned earlier. And also, Earth has features due to water vapor around here. And thermal emission is a very nice probe of the temperature. Typically thermal emission spectra are modeled using 1D. But as we have seen before, the thermal emission spectra can also include the information of the heat redistribution efficiency, and it could be there could be a horizontal gradient. And this could also additionally provide additional information about the planetary surface. To see this, we look at the thermal emission spectra based on the three-dimensional atmospheric structure calculated with 3D GCM, Rocky 3D, which has been developed at NASA GISS. And here we assume the movie is crashed. For rocky planets, we assume the rocky planets with an Earth-like 1 bar atmosphere, but without surface ocean. And in this case, the planet is tidally locked, so the permanent day side and the permanent night side. And this shows the time evolution of the thermal emission spectra as it rotates around the star. And so in this case, the permanent day side is very hot, and the night side is dark. And so how this three-dimensional structure affects the thermal emission spectra? The figures on the right show the three-dimensional atmospheric structure, where the upper panel shows the temperature map as a function of pressure and longitude from the substellar point. And here it's a temperature map as a function of latitude and longitude. And this is also a substellar point. An interesting point would be that the typical structure of the synchronously rotating planet is that, of course, a very hot permanent day side, very hot day side, but also there is some hot region here, and there is a thermal inversion very near the surface, as shown here. And so based on if we calculate the thermal emission from this structure, while we look at the planet at the quadrature, the red line is such a thermal emission. And this feature comes from CO2, but some weird feature appears around here. And this is actually CO2 seen as emission at the wing, near the wing of the absorption feature. And this is related, this comes from the fact that there is a strong thermal inversion layer near the surface. So although even the snapshot thermal emission spectra includes such information about the atmospheric circulation or the three-dimensional nature of the planet. Oops. And also, depending on the configuration, the overall spectral shape deviates from the black body emission for the one for us given temperature because of the horizontal gradient. And in some cases, this gradual decrease, so the red line is based on the three-dimensional structure of the synchronously rotating planets for certain assumptions. And in some cases, these features, the overall shape has some decrease toward the longer wavelengths. And this can, in some cases, mimic the broad water vapor features. And so to properly interpret the spectra, we actually need the really deep understanding of the atmosphere, which could be probed by time variation, for example, as the planet rotates around the star. And so the comprehensive modeling of the planet is really crucial in understanding the limited data available for exoplanets. Okay. So finally, I'd like to conclude with a summary and discussion. And in this talk, I have focused on how to infer surface environment of planets, particularly by looking beyond the atmospheric spectroscopy and focusing on the properties of the continuum and also time variability. Constraining the atmospheric composition through absorption band will be a first milestone, but we can potentially go beyond it. And we also discuss that the primary observation data of average spectra as a point source could be affected by three-dimensional nature of the planet or the property of the planet as a system. So I have also discussed that the nature of the solar system planets as benchmark cases, and seeking for the synergy between the accumulated insights into solar system planets and exoplanet observations. So the knowledge gained from studying our own solar system could potentially help us better interpret the data which we receive from distant world. And I see more room for further collaboration. And considering the limited amount of data and likely low signal-to-noise ratio, the interpretation tend to suffer from degeneracy. And this is actually already seen in the exoplanet data of Jovian planets, or gaseous planets. But in the case, the case would be severer for rocky planets because there could be potentially a wider variety of atmospheric properties and also evolutionary pathways. And so how best we can recover the surface environment of the planet from accumulating multi-angle data is and will remain to be key question. For this, sophisticated extrapolation of the processes known in solar system to other worlds remain to be studied further, and so that we can characterize a planet as a system. Okay, I'll stop here. Thank you for your attention.
Thank you so much, Yuka, for the fascinating and comprehensive talk. I'd like to invite anyone or everyone to come forward with questions. And remember that it's nice to see and hear you if possible. Do we have a first question? You can also, okay, and Anjali, go ahead.
Hi, yeah, thank you so much for the nice talk, Yuka. I was curious, so given that I guess for the sun, we are most sensitive to reflectance in the optical and the different types of surface features that we can see through that. I was wondering for M-dwarf planets, presumably will be more sensitive to reflectance in the near infrared. And I'm just curious what kind of surface features do interesting things in that wavelength range. I'm not so familiar with that.
I think the in the near infrared, the features from icy surface or the snowy surface would have prominent features in the near infrared. So it's something one of the important clues. And also, if you compare in the visible and the near and toward the longer wavelengths, although in the optical, the cloud and snow have relatively similar gray features, the snow becomes very darker in the near infrared. So this contrast can provide some interesting variation potentially, I think.
Yes. Do I see any more questions? You can use the raising hands feature in Zoom. I'll ask a question. I'm glad that you talked so much about the importance of looking at solar system objects as a ground truth. I think that's really smart. I'm wondering what we need to worry about if instead we are trying to synthesize albedo spectra from, say, lab measurements, where we're not actually measuring the whole surface, but say like different little minerals or different parts of it, and how if we try to mix that together, what we need to worry about.
Yeah, so basically the disintegrated spectra with raw SN means that we will be able to detect only very, very broad feature or some general overall trend. And so it will be the result of the mixture of different composition. And so understanding the reflectance spectra of certain materials is very important. But to what extent this can be globally covered, this can globally cover the planet is also crucial. And so material reflectance spectra is very important, and also more like a global feature we should probably focus on. Does it answer your question?
Yeah, I think I've just been like looking at kind of lab measurements of, say, different minerals, but I'm wondering how easy it is just to kind of average those to get what the disk of the planet would look like. I don't know, so I was wondering what you thought about that.
Yeah.
Do we have any more questions? Yeah. Yeah, Anjali?
Sorry to go again. If anyone else wants to jump in.
Yeah.
I thought it was really cool the NOMAD transmission spectrum that you were showing for Mars, and I was curious in the spectrum during the dust storm. I noticed that so you mentioned that the H2O ice feature is also high because of the transport, but it looked like the CO2 feature, even though it was more muted, like it was still peaking up at like higher altitudes than the non-storm scenario. And I was wondering why that is, and is there also some kind of CO2 transport that's enhanced?
Actually, we have not investigated to that detail, so we will check it later. But it's possible that this is sort of low resolution spectra, and it's actually a the high resolution spectra is averaged out, and so I'm not sure if it's really changing the optically thick layer when we look at the very high resolution. So, but we will check it later. Thank you very much for the comment.
Actually, can I ask another question too? I'm wondering if Io were an exoplanet, what could you constrain about its surface composition? Could you tell there was lots of sulfur, or could you just tell it was something bright?
Thank you very much for the question. I think Io is also another interesting example, and it has sort of diverse colors, and most of them are related to sulfur and and also frost, silicate frost. Sorry, SO2 frost. I think white SO2 frost and sulfur, yellowish sulfur color, and it has a very sharp feature in reflectance spectra. The sulfur species has very sharp features in the reflectance spectra at relatively short wavelengths. So the reflectance spectra dramatically increases at certain wavelengths, like red edge. And so if we can take the difference between these two two bands bracketing this edge, we can infer the presence of sulfur, I think. And so I think it's also very interesting.
Yeah, that's really interesting. Do we have any final questions? Last call for questions from the audience. Okay, if not, then I'd like to thank everyone for coming to this iteration of the Rocky Worlds discussions. And thank you again to Yuka, if we want to give a clapping reaction to show our enjoyment and appreciation for this talk. And our next Rocky Worlds discussion, which I hope you can all make, will be on the 5th of September. And that will be Alice Booth from Harvard CFA. He will be talking about protoplanetary disk chemistry. And thank you so much. I will leave the meeting now.